Okay, let's do one more example problem. Example problem 3. So far, all the examples that we have been doing, they're of different variety and they're representative of the kind of other problems that you will encounter in the homework. If you understand all the example problems that we do here, you should be in a good shape to solve those problems that we are not solving. Okay, so really it is meant to build your technical strength so as to be able to answer a variety of questions. Now, let's look at this problem. We have a circuit and we are given, okay, and we are given the omega, okay, we are given the omega to be 1.6 into 10 to the 6 radians per second. What are we supposed to find? We're supposed to find the impedance, the equivalent impedance of all of this circuit looking into the terminals AB. Okay, find the ZAB impedance at the terminals A and B. Now, if you have not seen this before, we are going to use this method called V-test, I-test method. Okay, we're going to use V-test, I-test method. When there is no direct way to calculate ZAB, what we do is, let me copy this really quickly, duplicate this. Okay, what we do is to apply a hypothetical V-test here, V-test, and we look at the current I-test that is going through the uh, circuit from the applied test voltage. Now, in order to find ZAB, what we do is to get an expression for V-test over I-test. Okay, this is our approach. We apply a test method and derive V-test over I-test. Okay, that gives us the impedance. Before we do that, let's copy this and duplicate this one more time and see what we can do here. Okay, duplicate this. Okay, okay. All right, so let's keep it simple. We'll duplicate this AB. This is 15I delta, 15I delta. So clearly we want to convert this into frequency domain. The first step is to convert all of this into frequency domain. So I'm going to write this as J omega L. Okay. Similarly, the capacitance here, I'm going to write it as 1 over J omega C. Okay. And this resistance remains the same. So all I'm doing is converting the impedance and capacitance from um, regular time domain into their impedances form. Okay. Now J omega L, which is also annotated as ZL, is J times omega is given to be what? 1.6 into 10 to the 6 radians per second. Okay. L is given to be 25 microhenry. 25 microhenry. Okay. Don't trust me? Go back and look at the problem. Omega is given to be 25 microhenry. Um, that's L, and omega is that. Okay. So if you do this math, you're going to see that this is J 40 ohms. Similarly, let's calculate ZC as well, which is 1 over J omega C. So plug in all of that. Omega is again 1.6 into 10 to the 6. And C is what? C is given to be 25 nanofarad. Okay, 10 to the negative 9 farad. You plug that in, you will see that this is negative J 25 ohms. Okay, so I'm going to write this as J 40 ohms. And this one is negative J 25 ohms. Okay, very good. Now we are ready to write this draw this in, okay, I'm going to clean this up. Let me clean this up really quickly. Okay, so I'm ready to write this. This is the frequency domain. Okay, this is the frequency domain impedance form of the circuit. Okay, here is where we apply the test method, the test voltage method. You see, because of the independent voltage source, there is no direct way to calculate the impedance here. So we apply a V test. Okay, and then look at the I test going. Okay, look at the I test that is going. Okay, so let's see. It's a pretty simple problem. Remember everything that you did in the steady state analysis. Okay, so we are going to do something very similar here. Step one is to apply KVL. Okay, apply KVL around the outside loop. Okay, around the outside loop, this guy. Okay, not the outside loop. Look at this loop here. Okay, that's the loop from which we are applying KVL. Okay, start at the bottom left corner, go through the entire loop and add up all the voltage drops, equate them to zero. KVL, right? KVL applies in steady state analysis as well. So I start with negative V test, and then there is a voltage drop of I test times J40 omega. That's the voltage dropped in this component. Okay, then there is this component which is plus 15 I delta. Okay, that's the voltage dropped here. Now what is the voltage dropped in this impedance? You see there is I test going in here, and part of it is going into I delta. So using KCL, you know that the current here really is, let me notate here, I test minus I delta. Okay, so that's the current I'm going to use. So which is I test minus I delta, all of that multiplied by negative J 25 ohms, right? So that's all the voltage dropped around this loop. Okay, now all of that equates zero. Very good. Okay, let's see how many unknowns do we have. We have an unknown of I test, we have an unknown of V test, and an unknown of I delta. So clearly one equation is not enough. Now let me write this. I'm going to write this as loop 1. Okay, this is loop 1. Okay, now let me duplicate the whole thing and see if I can apply another KVL. Okay, let's see. I'm going to erase this now. Okay. Now I'm going to apply KVL around this loop, around the outside loop. Okay, start at the bottom left. We are using the right hand loop. Okay, around the right hand loop, apply KVL around loop 2. So this is loop number 2. Right? Start at the bottom left. We have negative of I test. You see the I test is going from top to bottom. So there's a positive there and a negative there. So I delta times negative J25 ohms. So that's the voltage dropped in this capacitance. The current multiplied by the impedance. Then what else is going on? Then there is this I delta times 25 ohms. Okay, so there's a voltage drop of I delta times 25 ohms that's dropped in this resistance here that completes all the voltages dropped around this loop. That should equal 0. Okay, so now we have a set of two equations. So let's see, let me copy this again, or let me simplify this here. Okay, I'm going to write this simply as I'm going to factor out I test into J15 ohms plus I delta into 15 plus J25 ohms equals to V test. Okay, let me make some room here. I'm going to make some room here so that I can box this. Okay, let's see. I'm going to use this one as my equation 1. Okay, that's my equation 1. Okay, similarly, I'm going to simplify this one as well, this equation as well. Okay, that comes out to be I test times J25 ohms plus I delta times 25 minus J25 ohms. All I have done is factor out I delta from this guy and this guy. Okay, so there is a I delta times J25 ohms that's coming here. Okay, 25 ohms is coming here. So it's simply a mathematical manipulation we are doing at this point. Okay, so that equals 0. So here is my equation number 2. Okay, so we are going to have to solve this using MATLAB. If you followed the MATLAB in the previous chapters, you should be able to set this up. And then there is an example problem on how to solve complex numbers. Okay, now let's take stock actually. I test is unknown, I delta is unknown. So I test is unknown, I delta is unknown. So a lot of times I write I test. Okay, so two unknowns, but let's not forget this guy. Okay, there's another unknown V test. So we are going to simply substitute when we are solving. Okay, when we are solving uh, using MATLAB, plug in V test equals to 1 volt. Okay, just use a value of V test equals to 1 volt. Now you have two equations. Once you plug these two equations into MATLAB, you should see I test value equals 0.025 minus J 0.025 amperes, and I delta equals to negative J 0.025 amperes. Okay, we have I test, we have B test. How do we calculate ZAB? ZAB is V test over I test. Remember, go back to the very beginning of the problem. What did I say? The way we calculate ZAB is to apply a test voltage. Okay, let's apply a test voltage and get an expression for V test over I test. We are at that point now where we can calculate V test over I test. You see, V test is 1 volt and I test is what? 0. Okay, 0.025 negative J 0.025. Okay, now you can convert this into polar form and then you can do all the interesting mathematics. You'll see that ZAB is really 20 plus J 20 ohms, which turns out to be 28.284 angle 45 degrees. Okay, it's not surprising. You don't even have to do the math for the angle. Think about this. Your imaginary part and real part are equal. When your imaginary part and real part are equal, the tangent inverse of the imaginary part over the real part is really the tangent inverse of 1. And that's the reason why we get 45 degrees. You see, there is a method to madness. You can see that there is a intuitive way of understanding and doing a quick sanity check of your problems. But here again is the answer that we are after. Okay, what is the impedance ZAB? ZAB is 28.284 angle 45 degrees. Okay, there you go.